This is a video on cylindrical coordinates. The question states, find the mass of the solid with density rho of xyz equals the square root of x squared plus y squared that lies inside the sphere x squared plus y squared plus z squared equals 4 and outside the cylinder x squared plus y squared equals 1 and above the xy plane. So let's start by sketching a picture. We have the sphere centered at the origin of radius 2 and a cylinder centered at the origin of radius 1. So I sketch the sphere and I sketch the cylinder and I put the little man standing up and down, and I'm going to use cylindrical coordinates. I have a cylinder and a sphere, so it's either going to be cylindrical or spherical. The deciding point for me is going to be the density is the square root of x squared plus y squared that works better in cylindrical coordinates. So in that case, I'm going to be looking at a dz, dr, d theta. So I have my little man standing up and down, and I can see the little man's feet are at 0, and the little man's head is on the sphere. And the sphere, I can solve for z and say that z is now between 0, the xy plane, and the sphere, which is the square root of 4 minus x squared minus y squared. I can turn this into cylindrical coordinates, knowing that x squared plus y squared is r squared, and say that z is between 0 and the square root of 4 minus r squared. So now let's find the limits for r. And that, I look at my little man, and I notice the very farthest inward the little man can get is on the cylinder, which is r equals 1. And the farthest outward the little man can get is out on the sphere that has radius 2. So that's r equals 2. So I can say that r is between 1 and 2. So now for the limits for theta, that's how far around the little man can walk. The little man can walk all the way around this circle. So I can say that theta goes from 0 to 2 pi. So I also have a conversion factor that tells us that dz, dy, dx is always equal to r dz, dr, d theta. And then finally the density, rho of xyz, is the square root of x squared plus y squared. But the square root of x squared plus y squared is just r. So I can say that the density function of r theta z is equal to r. So I could put this all together as a triple integral, so that the mass is equal to the triple integral. Theta goes from 0 to 2 pi, r goes from 1 to 2, and z goes from 0 to the square root of 1 minus r squared. And then I have my density function, which is r, and then r dz, dr, d theta. So I could integrate this by hand if I wanted to. The integral of r squared dz is just r squared z, and I can plug in 0 and the square root of 1 minus r squared and get r squared times the square root of 1 minus r squared. Then I can use some techniques of integration, maybe trig sub, and integrate that, but instead I went the easy way out, and I used a calculator. And I found that the mass of the solid that has this density function that lies inside the sphere and outside the cylinder and above the xy plane is equal to pi times the square root of 3 over 2 plus 4 pi squared over 3. And I'm done with the problem.